So our final speaker in this session is Jonathan Pipping. He goes by JP. He's a second-year PhD student in the Department of Statistics and Data Science at the University of Pennsylvania. His research focuses on machine learning and statistical inference with applications in medicine, economics, and sports. He's also a member of the Wharton Sports Analytics and Business Initiative research team and was recognized as a 2025 Big Data Bowl finalist.
Okay. All right. Hi, everyone. I'm JP. Today, I'm going to be presenting my work with Professor Weiner, talking about blown leads, and sort of undermining maybe some assumptions, some intuition that we might have about it. All right. There we go. So we're going to look at a case study from 2 years ago, one that the people at UPenn might not be too happy about. But 2 years ago, the Eagles and the Chiefs played in the Super Bowl, and it was a great game, back and forth. Lots of drama, came down to last-second kick. But by the start of the second half, the Chiefs were behind, actually, by 10, and they faced a 3rd and 1 at their own 34-yard line. At this point in the game, ESPN estimated that their win probability for the Eagles was 78.4%, which is that red dot that you see at the top of the graph. We know that the Chiefs went on to win this game. In fact, the very next play was an explosive run, and the Chiefs would go on to score a touchdown, eventually winning 38-35. This is an interesting phenomenon, right? Something we see a lot in sports. A blown lead, right? 78.4%. That's pretty non-trivial. We want to understand, how rare is this to happen? How common or uncommon is a blown lead of this magnitude? Intuitively, if you ask the average bystander, right? Eagles, 78.4%. What percentage of the time, right, would we expect to see something like this? They would probably say, well, 100 minus that, right? You'd say 21.6% of the time, right? That's the percentage of the time we'd expect them to lose from that position. That's the intuition, right? But maybe that's wrong. Maybe that's wrong. To investigate this, the first thing we're going to do is set up the question, fundamentally, mathematically. So here we go. Win probability. What is it, right? Well, in theory, it tells you from a particular game state at some time with some score differential, how likely are you to win that game, right? In some senses, when we're estimating it, we're estimating a function of the game state, right? The game state could be your score differential, where you are on the field, maybe the players that are in, team strength, and then the time that we're evaluating this win probability. In a two-team game, and in fact in any game, the sum of the win probabilities in a multiplayer game, it's always 1. But in a two-player game, it's nice. We have only two players or two teams. We know that it's complementary. So if I tell you that Team A has a 60% win probability, you can tell me Team B's win probability. It's 40%, right? They add up to 1. That's a useful thing we're going to leverage throughout this. Now, we're interested in the eventual loser of the game. Our question is really how often do blown leads happen? That requires sort of thinking about who ends up going on to lose, right? We know in the Super Bowl from 2 years ago, the Eagles lost that one. And in the Super Bowl from this past year, the Chiefs lost that one. We know this, right? And so we're looking in retrospect. We understand that for the loser, at the end of the game, their win probability is 0. This is, again, another important thing we're going to leverage as we continue to move through this. Our quantity of interest that we're interested in is what's the maximum win probability that's attained by the team that goes on to lose. So in the Super Bowl from 2 years ago, that would be our big number, 78.4%. That's what we're interested in. We want to understand that distribution. Okay, now, estimating win probability, notoriously difficult problem. It's been done for many years. many different types of ways. As we've gotten more recent, it's been more ML. And some of the people that I've gotten to work with presented at this conference last time this conference was about that, right? About win probability, how difficult it is to estimate it, issues with effective sample size, selection bias, et cetera, et cetera, et cetera. It's real tough. So what do? Right? We have a complicated game state. We have team strengths. Those are all their own estimation problem. Instead of getting into that world, we say, let's simplify the problem first. Let's look at a toy example, some toy football or some toy basketballs. Build a toy little simulation version and see what happens in that. So we specify a pretty simple model for calculating win probabilities where we'll be able to write it out on math, or on a piece of paper, what the win probability is at each state. So what do? We say, two-team game, each team has an equal number of possessions. Okay? We set that. That's going to help us in some calculation. We also assume that team strengths are fixed and known. So we know the team strength, and the team strengths are parameterized by PA and PB. Right? These correspond to the probability that a team scores on a given possession. And then we say, right, we play this game out, fixed possessions, with these known probabilities, and if it gets to a tie, we just flip a coin. So we know the win probability at every state. It's this, right? It's the probability that a binomial random variable of the number of possessions you have left in the game, plus your current score, which is ultimately, that's a formula for your final score. So it's basically the probability that Team A's final score is greater than Team B's final score, plus, again, our overtime coin flip. That's all it is, because we have fixed possessions, we know what that is, and we know the strengths, the probability that they score. You can imagine in football, this corresponds to a touchdowns-only model. So you can only score a touchdown, and that has some probability. In basketball, you'd say made baskets. All right, now, for each set of parameters, the number of total possessions, the team strength, we do the following. We'll calculate the win probability at each game state. We simulate 10,000 games between these two teams. And then what we do is just pluck out our quantity of interest, the maximum win probability that the eventual loser reached. We know who the loser is, right? We observe the whole game. We just take the maximum from that path. Now, let's consider the distribution of ML, which is the maximum of the eventual loser, as we vary our parameters. Case number one is we have the team strengths are equal. So the probability of Team A scoring is the same as probability of Team B scoring. This is a fair game, or a 50-50, right? You have even odds at the start of the game. And then we have unequal team strengths, which is obviously way more common in sports. We have an asymmetric sort of win probability calculation. OK, here we go. At down columns, you'll see the probability of each team scoring. This is the symmetric case, where each team has an equal team strength. We have p equals 0.45, 0.5, 0.55. And then down rows, you see what happens as we increase n, as we increase the number of total possessions in the game. OK, across rows, the distributions look basically the same. As we vary the probability of scoring, holding constant the number of possessions, that distribution, very close, very similar. OK, that's interesting. What does that mean? We'll talk about that in a second. As we go down columns, as we increase the number of possessions, we see that our histogram starts looking smooth, almost. Almost like you could draw a line through it, like a function, right? That's interesting. OK, this is another version of that. This is a threshold plot. This is essentially, in what proportion of games did you reach a win probability above some point? It's the histogram in a different form. You'll notice it starts looking a little blocky at the start, but it starts smoothing out. This is sort of what we saw with the histogram. What are some things we could take away from this? Number one, when the probabilities are equal to each other, you'll notice the support is only from 0.5 to 1. Why is this? Because it's an even game. Both teams start at 50-50. You can't have a maximum below 50%. Next thing, holding n constant, the distribution of the maximum for the loser looks pretty identical across those probabilities, right? Across those different PAs, or equal to PB. This implies that the distribution of the maximum for the loser might not depend on what the strengths are, but what they are relative to each other. Difference, or maybe the quotient. Now, then we also saw that holding PA equals PB constant, the distribution of the maximum for the loser becomes less discrete. It actually starts looking like something continuous. Some of you might be asking, hey, maybe there's an analytical form. We'll get to that in a second. Interesting observation that we find, this sort of betrays our intuition a little bit. In about half of all games across our simulation, the losing team attained a win probability of 66% or more. That's interesting. We're going to keep investigating this as we keep going. The next case is the asymmetric case, where the team strengths are different. Again, this time we have the probability of team A scoring down columns, probability of team B scoring down rows. This diagonal represents fair games, even games like we saw before, for comparison. And the most extreme other ones, right, this is, you have 0.495 and 0.505 here. Very different team strengths, very different team strengths here. What do we see? As, compared to our fair game, as team strengths get further and further apart, you notice the spike, it gets higher and higher and higher. What does this mean? The team that's eventually losing, right, their maximum is very close to their starting win probability. We note that the left tail is getting smaller and smaller. The more extreme the difference between your teams, the more the stronger team dominates. The more, the losing team doesn't get to a high enough win probability over the course of the game. That's interesting. Also, notice that if we look at these pairwise comparisons, so look at 0.5 and 0.495, right? And this one, those distributions are the same, right? Same here and here. If we hold constant the difference between team strengths, the distributions are the same. This tells us something, again, about what we're going to expect for what this distribution looks like. It depends on the difference in team strength, the absolute value of the difference in team strength. These are the threshold plots again, another version of that. Here we go. OK, when we have an asymmetric game, we find that the support of the maximum is the minimum of the two strengths to 1. Why does this make sense? OK, let's say a game starts at 60%, 40%. What's the lowest maximum win probability of the loser? It's 40%. Right? If the weaker team goes on to lose, their maximum could be 40, but you're never going to have something lower than that. What's something else we find? Holding n constant, the distribution of the maximum for the loser is constant across equal differences in team strength. So essentially saying, you could have a probability of scoring of 0.5 and 0.6, and if you made that 0.6 and 0.7, the distribution is the same. This implies, again, that it depends on the absolute difference in team strength. Finally, we find that holding n constant, the distribution of the maximum for the loser is increasingly right-skewed. Right? You get a much higher mass in low win probabilities the greater that difference is. OK, now, we saw we are getting close to something like a continuous function. We want to find that. Right? So our hope is to find a closed form solution for the distribution of the maximum in our simplified model. To do this, we define some parameters and some random variables. So here we define x as the score difference at a given time. This f represents the sigma algebra. It's just the set of information available, basically what we know about the path as we continue through the game. And then we have y, which is our outcome, what we care about, right? The event that team A wins the game, right? Then, from here, we do something, this is a measure theoretic expression, but essentially we say we're going to express team A's win probability at each time step as a Doob martingale. I'll get into sort of what this means in a second, but essentially we just say that your win probability is the expected value of your outcome, right? How often do you win? Your outcome is a 1 or a 0, so your expected value is your probability. From here, we define a couple more things. We say MA is the maximum that our team A attains. And we define this TX as a stopping time. It's the first time that a win probability would exceed some pre-specified win probability. We know from stochastic theory that since we have a stopping time, we can use the optional stopping theorem. And this is going to help us get something like a closed form solution. OK, here we go. Start getting to the fun stuff for some people. The distribution of the maximum for a given team satisfies this. This is just the maximum value that they attain over the course of the game. This is your closed form distribution. And you notice it scales with 1 over x. Also notice that for in this case, right, this is just the maximum that a team attains, right? That includes the chance that they win. What's the weight on the chance that they win? Their starting win probability. What's our next quantity of interest? Okay, so we're trying to get the maximum of the eventual loser. We don't know maybe who that is at the start of the game, but what we can get is say, what's the distribution of the maximum that team A attains, knowing that team A loses? This is easy. This is findable. You do some, conditional expectation stuff, and this pops out, right? We notice something like this. This is the form for the conditional distribution of the maximum for one team, given that they lose. But that's not really what we want, right? We want the maximum for the eventual loser. Now, again, you might be wondering, why am I saying team A, team A, team A? What happened to team B? Okay, we know that team B, the probability that team B wins is 1 minus the probability team A wins. So we'll only look at one side of this for the most part. What's the form look like? Well, you can imagine team A's starting win probability of P0. That's in there, right? That's in our function. All we have to do is replace that with 1 minus P0, with the starting win probability for team B. Okay, but again, that's not really what we care about. We care about the win, the distribution of the win, maximum win probability attained by the team that goes on to lose, right? The team that goes on to lose. What is this? This is a mixture, right? It's a mixture of two possible outcomes. Team A loses or team B loses. And those have some probability, some known or estimated probability. So what we do is we just say, hey, let's take these distributions, the distribution of the maximum some team would attain if they lost. Let's weight it by the probability that they end up losing the game. And that gives us some distribution for the eventual loser. Something to note is that in the region of, these regions, right, between your starting win probabilities from 40 to 60 in our 60-40 case, right, only the underdog can contribute to that. Because the maximum, the win probability starting for the favorite is 60%. So for the loser, right, from 40 to 60, that's dominated by the loser. So we're going to have something like a piecewise relationship. The loser is going to contribute losses in that 40 to 60 region, and then both teams will contribute, in the higher region. So this is our third theorem. This is a nice one. This gives you the maximum win probability of the eventual loser. You do this mixture distribution, and this pops out. Cool. That's our quantity of interest. But, maybe point of concern, and you might have seen this on the other ones as well. This is inequality. We don't have equality here in our, in our CDFs. We don't. Why? Why? Well, we're dealing with a discrete n case, right? Discrete number of possessions. You can imagine that, there's only finitely many states that are possible if you have a finite n game. And so your win probability could jump over some level in the final step. So we can't really guarantee where the mass lies. For example, consider a one play game, right? Where, let's say, equal probabilities for simplicity. The win probability of team A at time 0 is 0.5, same for team B, and then they just jump to 0 or 1. All the win probabilities in the middle are crossed on the next step. Okay, so that's why we have our greater than or equal to. We can't really specify, exactly where the mass is. So what we need for this is something called continuous sample paths, essentially meaning you have something close to a continuous path for your win probability over the game. How are we going to get this? We let n tend to infinity. Increasing the number of possessions gives us something closer to a continuous win probability, where win probabilities are very close together and there's a lot more game states. In this limit, what we can do, then we can derive these exact forms. So we do that. We set everything up the exact same way. We have our score differential, our information sets. We have now a new parameter, which is our difference in scoring probabilities. We know this matters. We have the variance in our scoring. And then we have, by Donskir's invariance principle, we pass this to a Brownian motion. Okay? Brownian motion has some really nice statistical properties that we invoke to get nice closed form distributions. Okay? Again, this is more defining things. The terminal event, what it converges to. We have the event that team A wins the game is defined the exact same way. We have the starting win probabilities defined the exact same way. Notice in the Brownian motion sense, it has something to do with the normal CDF. And then we can define team A's win probability the exact same way. Define the same qualities we did before, optional stopping, and now we have a path to a closed form win probability for our toy model. Here it is. It takes on the exact form of the win probability in the discrete case with the specialization that obviously we're working in Brownian motion, things are going to be normal. This is the distribution of the maximum for a team, including, they could win. They could win the game. This is the conditional distribution given a team loses, right? And you'll notice, again, we have the exact same form as we did before, but since we're using Brownian motion, we get something in terms of the normal CDF and the difference between the two team strengths. Distribution for team B, we know it's the same, it's just a 1 minus, and then we use our mixing to get the distribution of the eventual loser. Again, this is our quantity of interest, our distribution of interest. Cool. Same piecewise relationship. It depends on the starting win probabilities of the teams. Awesome. So in evenly matched games between equal strength, we have the following. If each team's starting win probability is 50%, then the distribution of the maximum win probability for the eventual loser is this. The CDF moves with 1 over x. And you can imagine the density moves like 1 over x squared. What does that look like? Like this, right? That's pretty similar to what we saw in our histograms from our simulation. In unevenly matched games, we get the following. We have different starting win probabilities, and we define it piecewise. And then here, right, from here, you have between the two starting win probabilities, only the underdog's maximum contributes to that. And above that, both teams' maximum will contribute. So you get that nice mixture that we talked about. OK, now for the good stuff, for the real stuff, right? Math is really clean. We have a nice simplified model. It works nicely. We get these closed form distributions. And if you let n tend to infinity, which it never does, then we have a great closed form, right? We know the distribution of the maximum for losing teams. But we still have a pretty major simplification. Let's go back to this. Let's critique our own work here. First of all, scoring isn't binary, right? A lot of the time. In football, you have touchdowns, you have field goals, you have extra points, you have 2-point conversions. And then if you want to go even further, more granular, you have first downs, you have field position. Again, so many different complications. Team scoring probabilities might vary throughout the game. You can imagine at the end of the game, right, when there's 20 seconds left on the shot clock, and a team is up by 10 in basketball, and they're dribbling it out, what's the probability they score? Right? It's close to 0. It's not the same as it was over the course of the game. Same in football, right? Lots of sports work like this. The scoring probabilities might vary over the course of the game. That's something that we didn't account for. Teams, they have an unequal number of possessions a lot of the time, depending on how you count possessions in basketball. If you have turnovers, right? Teams don't really get full chances to score a lot of the time. Furthermore, injuries, game strategy, other factors, they matter a lot. And game states are super complicated, like I talked about before. So again, we have a pretty unrealistic model. It's pretty simple. It doesn't really, approximate. It doesn't attempt to approximate real life. Let's take a look at what our distribution says about real life NFL games. Let's see how it compares to what we see in the data. It's pretty good. It's pretty OK, right? This is the empirical distribution of the maximum win probability of losers in the NFL from 2002 to 2024, which is where the data supports. We have 672 games, not a small number, right? And again, I have the mean and standard deviation up there for you guys. Look at that distribution. It's not that bad. It's pretty close. Notice I've labeled the density here. This is the density function. So you'll see it's of order x, 1 over x squared, not the 1 over x. It's just the density. All right, let's look at the threshold plot that corresponds with this. Pretty close together. Not bad. Now, notice I've qualified this. These are evenly matched NFL games, games where the spread is less than 2. So our evenly matched model would say, this applies. Matches pretty closely. And we see in real games the phenomena that we saw in our simulation. In about half of games, the losing team is reaching 2-to-1 favorites, right? Minus 200 favorites. Half of games. It's pretty impressive. Let's look at uneven games. Uneven games, we have our piecewise function. These are real NFL games. You'll notice, it's maybe a little less perfect, but it's pretty good, right? It's pretty close. You see that piecewise behavior. We see it shoot up at the starting win probability for team 2. And this is even more sample, 1,005 games. These are games where the spread is exactly 3. So there is a non-trivial difference in win probability here, starting win probabilities. This distribution, you might be wondering, hey, what's this drawn line? You drew a mixture distribution. It's not really as clean. How do you pick P0? P0, right, our starting win probability is just the observed proportion of times that we saw a 3-point favorite win, which is about 58% over the last 28 years. We plug this in to our distribution, get a pretty clean form. If we look at the threshold plot, which is the equivalent version of this, right, the CDF version of this, they're not that far off. Right? Our model is doing OK, pretty good actually, against real data. So what does this tell us? What does this tell us about football? What does this tell us about sports? What does this tell us about how we think about win probability? Right? First, the brag, the humble brag. Our simple model did OK. But another thing, an important thing, is that blown leads, they happen all the time. And not just small blown leads, not 51%. We're talking 60%, 70%. In half of games between evenly matched teams, the loser is exceeding 67%. Exceeding. Right? 2-to-1 or better. Maybe 75, maybe 70, 75, 80. In a lot of games. A lot. Another thing to think about, and this is how we think about win probability, think about winning, when we condition on losing, when you look at a game in retrospect, look at a game after it's happened, the distribution of outcomes is very different from when it is going into the game. They're very much not the same. Right? It's not what you'd expect. It's a 67% means 33%. It doesn't work that way. When you condition on some outcome, we have to account for that. You have to think about that when we do our analysis. Back to our case study. In the Super Bowl from 2 years ago, the Eagles reached a maximum win probability of 78.4% before ultimately losing. In case you're wondering, the spread of the game was 2. So this falls sort of in our pretty close to evenly matched setting. From this position, assuming a well-calibrated model, which is always up for scrutiny, it's true that the Eagles only had a 21.6% chance of losing the game. That is true under a well-specified model, a calibrated model. However, the event that the eventual loser of that Super Bowl would reach 78.4% before losing is much closer to 30%. Provably so, mathematically and empirically. Awesome. That's it. Thank you guys so much.
We'll take time for a question. If Mark throws a cube at you, you can either make a comment and ask a question or throw it back at him, one or the other. Questions? Yep, in the back center.
I'm not going to throw it at you. Well, maybe I will. Hey, that's fine.
Thank you. This was awesome. Obviously, you're dealing with a very clean setup, like you mentioned. Did you think at all about the difference in variance between the two teams, or when you're thinking about this? Because you can have really high-risk team and a much more consistent team, and how that influences the distribution of outcomes.
Absolutely, yeah. We assumed a very simple model that only depends on the strength parameter. But you can imagine a more complicated distribution where we have more uncertainty around some teams than others. That would be a complication. That's something we could add in. We might get a more calibrated model, but we might get a less tractable mathematical form, which is why we made that choice. But if you want to make that choice and write the paper, you're more than welcome to. I think it's a decent idea.
All right. One on this side, Mark. And we'll end with Ron.
With their hands up?
We're going to make Mark move around a little bit.
Thank you. For starters, very interesting presentation. Really appreciate it. Something I wanted to ask about is you're looking a lot at spreads and trying to determine team strength differences because of that. Did you consider home field advantage at all when you were looking at that? There's kind of the old adage that typically home field advantage leads to at least a 3-point swing on the point spread. So I was curious if you considered that in your research.
Yeah, so that is generally, I'm not sure if we have anyone from Vegas here, but generally home field advantage, is presumed to be baked into those spread numbers. We sort of tried to, take that into account by using the spread and, similar market things for team strength to get a proxy for that. If you wanted to study that, that's its own problem. There's a lot of literature in that and a lot of maybe interesting things there.
One last question, Ron.
All right. Okay, it's working. Great talk. My question actually is thinking of another use case for this where, like, even though you came up with a simplified setting, the win or the frequency of observing the loser's maximum win probability should still behave this way. And something like the NFL faster model, I would think, is flawed in many different ways. So could I consider this theoretical distribution as another evaluation metric of my win probability model?
Yeah, potentially. Assuming that our model is well calibrated, then you could compare it against ours, and that would give you sort of a barometer for, hey, is our model wrong, or maybe are the odds wrong, right? You could also look at that too. Are our measurements of team strength incorrect based on what you'd observe? I think there's a lot of use cases for this in sports, finance, anything where you have random walks and, that you want to quantify.
All right. Let's thank JP again.